Hi there, my name is Aaron Lancherman. I'm a professor of electrical and computer engineering at Georgia Tech. So far, all of the partial fraction expansions we've done in the summer 2020 offering of ECE3084 signals and systems have given us real valued roots. Here, we're going to see what happens when we get complex roots. So let's find the roots using the quadratic formula. I'll have minus b, which is minus 4, plus minus b squared, which is 16, minus 4ac, which would be 4 times 29, all over 2. So I'll have over 2 minus 4 plus minus, let's see what I have here. I'll have a 4 that I could factor out, which would give me a 2 outside of the radical, leaving me with a 4 minus 29. And this is square root of minus 25. All right, so here I'll have 4 divided by 2 with a minus in front, which gives me a minus 2. The 2's here cancel, and I'm left with plus minus j, because I'm taking the square root of a minus 5 as the square root of 25. All right, so now we can write out the factors. We have s plus 2 minus j5, and I'm putting a minus here because I like to actually put the root with the positive imaginary part first when writing out these factors. It technically doesn't matter, but you'll see why I like to do that in a little bit. And then the other factor will be s plus 2 plus j5, and that corresponds with the root with the negative imaginary component. So then the partial fraction expansion will look like a over s plus 2 minus j5 plus b over s plus 2 plus j5. I'm actually going to invert this Laplace transform 2 different ways. The first way, which I'm doing here, is a straightforward application of the residue method. The second way will involve completing the square. All right, let's find the partial fraction expansion coefficient a. The residue method will tell us to take 10 over s plus 2 plus j5, because the cover-up method would tell us to cover up the term with the minus in front of the j, and evaluate that at the root, which is minus 2 plus j5. And this will give me 10 over, let's see, when I plug minus 2 in here, the 2's wind up canceling, and I wind up with 10j in the denominator, which is just 1 over j, which is minus j. Oh, that's kind of nice. Here for b, we'll have 10 over s plus 2 minus j5, because the residue method in this case will tell me to cover up the term with the plus in front of the j. And evaluating this at the root, which is minus 2 minus j5, it's quite similar. I'll have 10 up here. The minus 2 cancels with the 2 when I plug it in, and I'll have a minus 10j in the denominator, which is like minus 1 over j, which is equal to j. And this is the first instance of an important property we'll see, which is that these cases where you have 2 roots that are complex conjugates of each other, the partial fraction expansion coefficients will also be complex conjugates of each other. So in this case, I could have just found A or found B, then I would have automatically been able to figure out the other one. But sometimes these computations can get a bit sticky, and if you have time, it's useful to try it both ways and then see if you get this complex conjugate property, because if you don't, that's a sign that you definitely did something wrong somewhere along the line. Now, if they are complex conjugate pairs, that doesn't automatically mean that you did it right, but you would be hard-pressed to make an exact matching set of errors that would give you that property. Usually, I would turn these into polar form. Here, I'm just going to go ahead and leave them as rectangular. So let me take them and plug them in for the A and B here. We'll have minus j and then a plus j. And come to think of it, when you see the direction that this derivation is going to go, it might actually have been easier to leave it with j in the denominator. But let me keep going with this path. Okay, so now let me invert this Laplace transform. I'll have a minus j constant, And then I could write this as e to the minus 2 plus j5 all times t. Remember that our Laplace transform pair with the exponent, it's fairly general as to what it will let you do. And then I'll have a plus j e to the minus 2 minus j5 t. And really this should technically have a ut on it, and this should have a ut on it too. We'll do my usual for t bigger than or equal to 0 later on. Let me factor out this e to the minus 2t. So I'll have e to the minus 2t times. So actually, I like the idea of putting the j back in the denominator. And while I'm doing that, to get rid of the minus sign, let me put a 2 here and a 2 here. This is just something I'm doing for this particular special case of this particular example. This doesn't always work. The fact that I have this 2j down here, you should be able to look at that and it should lead you to realize where I'm going with this. So I've got e to the plus j 5t, and then I'll have minus, if I put the j back in the denominator, I'll put a 2 here and a 2 here. Again, you'll see where I'm going in a second. E to the minus j5t, and all of this will have a ut that I'll factor out here. Okay, now this should be fairly obvious at this point. The reason I wanted to put the 2j down here was, if I think about that 2j, let's look at what I've got. I've got e to the j stuff minus e to the j stuff. So that's going to give me a sine using the inverse Euler's formula. So I'll be able to write 2 out in front, because I needed to put one there in order to pull off using the inverse Euler's formula. Then I'll write sine 5t ut. Again, I want to put in this caveat for t bigger than or equal to 0. We're not really saying anything about t less than 0. Now, usually in this course and in ECE 2026, we write sinusoids using a cosine form. I'm only writing it as sine here because it looks particularly nice that way. Another way to think about doing this derivation would be to take these j's here and go ahead and write them in polar form as e to the minus j pi over 2 and e to the j pi over 2. So how would that change this derivation? Well, it really wouldn't. We're basically saying the same thing. This would now be e to the minus j pi over 2. And down here I would have e to the minus j pi over 2. And then I'll have e to the j pi over 2 without the minus sign. And then if I looked at it in this form, I would just remember how to turn these kinds of expressions back into a cosine using the inverse Euler's formula for the cosine. And I'll write cosine 5t minus pi over 2. And I write the minus here because I get the phase of my cosine from the term associated with the positive frequency. And of course, you can turn this into a sine and back using trig identities. So that's just another way to view it. So earlier I told you that I would show you another way of inverting the Laplace transform. Here I'm going to rewrite it. Let's rewrite it as 10 over s squared plus 4s. And now I'm going to write 29 in a strange way. I'm going to write it as 4 plus 25. And the reason I'm doing that is because now I can take this and rewrite it as s plus 2 squared, because if I multiply all this out, that gives me these terms here, plus 25. And now I can remember that this is a Laplace transform we've derived previously that says e to the minus at sine omega naught t ut Laplace transforms into omega naught over s plus a squared plus omega naught squared. Okay, so I can match 2 up with a, so a equals 2. And then I can match 25 up with omega naught squared. So omega naught squared equals 25, which means that omega naught equals 5. And then I could take the 10 here and rewrite it as 2 times 5. So now I have everything matching up. So now for my final answer, I can write yt is equal to 2 times e to the minus, what was A? A is 2. So it's e to the minus 2t. And then I'll have sine 5t, because 5 is omega naught, ut. And again, I usually like to say for t bigger than or equal to 0. And that matches what we found earlier. Now, this completing the square trick looked like it took a lot less work than the residue method I just did. But this completing the square trick doesn't always yield a procedure that winds up simpler than just straightforwardly applying the residue method. It depends on the problem.